So, finding this Taylor polynomial. Again, there definitely is a brute force method here, but then there's a clever way. I hope you're realizing, like, if you write out first, maybe like what the Taylor polynomial would say, maybe we should do that here, okay? So pause for a second. Pause for a second. So the Taylor polynomial, in general, should be f of 0 plus the derivative evaluated at 0 times, help me finish that, times x to the first divided by, if I wanted to write it, 1 factorial, which is just 1. So if I wanted to put it there, I could. And then the next term, so the second derivative, all of these are always evaluated at 0. It's going to now be x squared. Now it's 2 factorial, which is just 2. And I need to keep going. So third derivative, fourth derivative, times x to the fourth, 4 factorial, fifth derivative. So this is what I just asked you to write out. Right? This is what I want. So first, that's the definition of the Taylor polynomial. That's what we looked at last time. Hopefully that's easy. The x's and the factorials are easy. The derivatives for this are not. How do you find the derivative of x times sine of x? It's product rule. So in this step, like f of 0, that's actually pretty easy because that's 0 times the sine of 0. So, but it's this derivative. So if I think about this derivative, so I'm going to have the first times the derivative of the second, derivative of sine is cosine, plus the second times the derivative of the first. Now I need to substitute 0 into that, and what's the answer? I heard 0. Is that right? So if this is 0, then this piece would all drop out then, right? But for this piece, I would now need the second derivative. I said 0 there, that should be x. So the second derivative evaluated at 0. So the second derivative, well, this is a product rule again, right? So first, derivative of the second minus sine plus second, derivative of the first, derivative of sine is cosine. I get another cosine. What's all that turn out to be? At 0. Sorry, Henry. Yeah, there's a 2 cosine x. Cosine of 0 is 1, so 2 times 1 is 2. This piece is 0, so that looks like it's 2. I think there's a 2 right there. Are you with me? And now the third derivative. Well, I'm going to get another product rule again, right? Like, do you see how it's not necessarily difficult, but there's a much more elegant way to think about this Taylor polynomial. So here's what I want to back up and do. So here's the function that we are trying to understand. Right? That's the function that we're trying to understand by writing a Taylor polynomial. So how about this? Could you write the 5th degree Taylor polynomial for just sine of x quickly? Like if I had just said, okay, g of x is sine of x, and I wanted the 5th degree Taylor polynomial for that. Could you do that without taking all the derivatives? Do you know which one it was? Was it the evens? Was it the odd? Is there a constant term to start with? Take 30 seconds and write that down. If you have to look it back up, then look it back up, then write it down. That is definitely one that we need to have memorized. It is going to come up often. What is the sine of x? And if you don't know it, or like on the AP test, if you get stuck, I guess you could make it, but that's just time consuming. Okay? Because you could take the derivative, derivative sine, cosine, minus cosine, et cetera, et cetera. Now, I'm going to think of it not as the Taylor polynomial, but as the Taylor series. And if you remember what I said on whatever day, Tuesday, I guess, that the series is all of them. The Taylor polynomial is through 5. But if I only wanted you to write through 5, couldn't we just say plus dot dot dot, and that would be the series? That's the only difference. Okay? So start me out. What would the 5th degree Taylor polynomial be for just sine of x? What is it? Is sine the evens or the odds? It's the odds. Sine is the odd function, right? It's symmetry about the origin. So that's one way to maybe remember that the sine function is the odd powers. Now, if you think about this constant that's sitting here, okay? So when I think about these odd powers, sometimes people get confused, like, okay, is this the one that has the plus 1? Or is it the cosine that has the 1 with it? Is there a way that you could remember that? Does this one have the constant or not? It doesn't. Why not? Because it's odds. Tell me what you mean by that. Yes. In fact, when you think about a constant term, isn't that really x to the power 0? Which is an even number. 0 is an even number. So that's why it wouldn't be there. Brendan? Yeah, so we could think about like that point, because that point is that first value as well, right? So if we think about from the Taylor polynomial, that first f of 0 would be the answer. So thinking about where the sine curve or cosine curve is would also be it. So that means this is starting really at 0. Now, is it going to be 0 plus? Is the first term plus, or is the first term minus? Somebody else? You can look it back up. So what is it? Anybody? It's plus. So if it's plus, so plus what? X, it's got to be x to some power. So it's got to be x to the first. Is there a coefficient here? Any coefficient? Anything I divide by? If I wanted to put something there, I'd put a 1. Now, why does this start with a plus? Because maybe that's the other thing to pay attention to. Because, again, if you're trying to memorize this and you remember it alternates, it's going to matter if you think it starts with a plus or a minus, right? Like it still could alternate either way. So give me some reason. So you're in the middle of a test and you're like, oh shoot, does sine of x, does the Taylor polynomial start with a plus x or does it start with a minus x? How could you sort it out? So thinking about how the graph is behaving, because when you think about like his hand, what he was motioning there, isn't that really a derivative thought about how the graph is behaving? Because aren't we going to take the derivative of this to get that coefficient? Right? So if you think about how the graph is behaving, it actually then gives the answer, or hopefully you remember the derivative of sine as cosine. Anyway, so next one. What's the next pieces here? X to what power? Third, 3 factorial, fifth, 5 factorial. And that's really what I wanted you to write here, so I should stop. So that's the 5th degree Taylor polynomial for just sine. And again, I'm not really answering the question yet. Okay, I'm reminding us of that. So, but here's then something that's true. Sine of x then is the same as this. And this would be the dot 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 forever and ever and ever, because if I cut it off somewhere, I shouldn't be using an equal sign. You should write this whole thing down in your notes right now. Because there's a really clever way to get what I'm asking for in the original question today. What do you mean? Close. Simpler than that. How may I say it differently? What is the series for x? Nope. It's just x. Let's do that in a second. But let's maybe not think of it then here as a series. How about this? Like, isn't this really a polynomial by itself already? Like it's an x already? So I don't really need to write a Taylor polynomial to represent what the polynomial x is. In fact, it would just be x. So how about this? If these two things are equal, shouldn't x times that be x times that? So x times the sine of x should be x squared minus x to the fourth over 3 factorial plus x to the sixth over 5 factorial minus x to the eighth over 7 factorial plus dot, dot, dot. So if I wanted through degree 5, now that also might seem like a strange question, right? Because when you're looking at that, well, I don't see a degree 5. Well, weren't we noticing a minute ago that there was a bunch of zeros? Like when we were taking those derivatives initially, like back here when I started actually doing the derivative, first derivative, second derivative. So you would actually just then include those pieces here, okay? If you wanted to put a 0 term in, you could, like a 0x to the fifth term, you could do that, but it would be implied even if you wrote it. So here's what I want you to take away. Like, just like we could take a power series and build a new power series by doing something to it, we can do the same thing with these Taylor polynomials. I can generate one, and then I can manipulate it to get new ones, okay? Questions, anything I said so far? Nana, I want to deal with your question there that you asked me, or you stated, about calling x the series, which we could. So if I say this function, f of x equals x, and I say construct the Taylor series for some power, why don't you do that? So let's say I wanted the, let's say I write something like this. What would you write? What's f of 0? 0 plus, what's the first derivative? 1. The derivative is 1, but it's going to multiply by x, divide by 1, plus second derivative, 0 times x squared over 2 factorial. But wait, isn't everything else going to be 0? Do you see it actually is just the same function? So that's actually going to be true even if it was something like this. So let's try it for this function. And in some ways, it should make really perfect sense, because aren't we taking a polynomial to approximate some other function? That's what we're doing with a Taylor polynomial. So what better to approximate a quadratic than the quadratic, right? So what's f of 0? 6 plus, what's the derivative? 2x plus 4. Evaluate that at 0. That's 4. X to the first divided by 1. Do you see how I'm getting that next term? Plus, now I need the second derivative. So that was 2x plus 4 was the first derivative, so that's 2. So 2x squared divided by 2 factorial. Wait, that's exactly the same function I just wrote. So that would be a good takeaway that when you think about a polynomial, the Taylor polynomial for the polynomial is the polynomial, right? It just is the same thing. All right. Let's see. So what I have here are, I should copy this before I draw all over my static notes. I want to have here several other examples of what we might see from AP tests centered around this thought of Taylor polynomials. Okay? And what I have here is really a different way to view, or a different way the question, I should say, is asked. So, worth jotting down. So here's P of x. P of x is 3 minus 3x squared plus 6x to the fourth. That is a fourth degree Taylor polynomial. Well, okay, sure. And then it says it's centered there at 0. Okay, sure. You know, we should have probably saw those things because I would have seen some quantity there, right? I would have saw an x minus 3 quantity squared. I don't see that. They're telling me information that's really unnecessary. I would have assumed it. But then here's the question. What is the value of the fourth derivative at 0? What is the value of the fourth derivative at 0? Now, I hope we are all looking at this term, right? But the answer is not C. It's not 6. Because isn't there actually two things that would have combined together to produce this value of 6? Talk about that at your table. What is the answer? What is the fourth derivative for the function that I can't see evaluated at 0? They're not saying the fourth derivative of p. Why isn't it 6? When I take the derivative, I multiply by the power. So there should be an additional 4 factorial involved in the answer. Somebody say that differently. So you're kind of thinking about the process going forward of like, I'm taking the derivative and I do that 4 times. There would have been a 4 factorial there somehow. There's another way to think about it in the other direction. Did anybody think of it this way? That shouldn't that be created by a calculation that looks like that? How does that confirm actually the comment that he just made that we need to multiply by 4 factorial? He's thinking of it a little different, but these are both confirming that we need to actually take this coefficient. If that coefficient is this whole thing, then that number should be 6 times 4 factorial. Talk me through that. Wait, is that too easy? Is that why you're just sitting there? Too easy. I'll just go on. Siri says no. Run it. Yeah, I like this like algebraic approach to it of like solving, because if this is the thing I'm trying to solve for, Well, now I can really easily see that additional 4 factorial. Okay. Don't know if I understand your question totally. Yeah, and I understand. I think I got it now. So, how about this? Is there any guarantee that f of x is a polynomial? F of x. Could I have started with a function f that was not a polynomial to ask this question? Maybe is the right answer. I could have, right? So couldn't f be something, if you think about what we just wrote down here on the last screen, f doesn't have to be a polynomial. Like when I'm making this here, and we end up writing, sorry, that's not yours, this here. Like I can end up seeing something like here, down here, right here. I can see something that looks like a polynomial, right? Because there's so many terms to it. And that's why I don't want to necessarily think about that the fourth derivative like should have been, like I don't want to think of a power there that was a polynomial, that power's coming down, because it wouldn't have to have been that way. Does that? I feel like I didn't totally answer your question. I just don't want this. I don't want you to look at this and go, that this function f was a polynomial, and if I take the derivative 4 times, then there would be a 4 factorial there. Now, it does kind of work that way because the Taylor polynomial is going to be constructed in that manner. So I think it's probably, if you just go from the definition of what the Taylor polynomial says, we should have a term like that, and I think that's why I go to that as our answer. Okay? So if you want to think of it differently and get the same answer, I'm happy to let you. How about this one? What is the coefficient of the x squared term for sine squared of x? This is worth writing down in your notes because we're going to approach this in a different way as well. Again, there is a clever way to do this, and there is a brute force way to do this. I don't think we probably want, like we could, I guess, take the derivative here a couple times, and that's not too bad. Okay. There's usually a question like this on the free response that might be a little longer. Like if I would have said the x cubed term here, like I'm going to make that really painful to think about the derivatives. Because what's going to happen is as you start thinking about this and you're taking the chain rule and then you're going to have a product rule and then you're going to have product rules inside of product rules, and these, like, it becomes messy. So I want to think about, again, this. Like sine of x, we think we know what it equals, right? You should know that. You should be able to write it down right now in your notes. Do that. Write down right here what sine of x should be, first term. Next. X over plus x to the fifth, 5 factorial, minus dot, dot, dot. So, a minute ago, when we wanted x times the sine of x, we just multiply both sides by x. So if I want sine squared, couldn't I like square both sides? Now, this isn't a great way to get maybe all of them over there, because that could, like, think about that multiplication. Doesn't that seem a little confusing? Like, because it's a dot, dot, dot. But you actually know some of these first terms. So what if I wrote it out, like thinking about like distributing? It would be, this dot, dot, dot times another one. Dot, dot, dot. Okay. So let's suppose I said, let's multiply this out. Okay. So we are actually writing right now the series for sine squared, aren't we? Right? If I know what sine is, and I square it, I've got to get the series that's corresponding to sine squared. So x times x times this, so there's a minus x to the fourth over 3 factorial. And I'm going to stop there because I guess maybe I'll go one more. So this is a plus x to the fifth over 5 factorial. I'm going to start multiplying this out. So this one. So I'm going to stop. I know that there's more that's going to happen here, but obviously I'm not going to be able to write those all out. But let's look at this next blue multiplication. It's going to be a minus x to the fourth over 3 factorial, isn't it? And then if I go one more, do you notice that's a plus x to the sixth over 2 times 3 factorial? I'm sorry. 3 factorial times 3 factorial. Just multiplying the fractions. Wait, do you know the answer to the problem? We actually knew the answer to the problem several minutes ago if you knew what this was asking. So what is the coefficient of x squared in the Taylor series of sine squared of x about x equals 0? 1. If I wanted the coefficient, I could ask this question though, and this is the question that is going to come up here in a minute. If I would have changed this and said, what's the coefficient of the x to the fourth term? Is that possible? Like I see an x to the fourth and I see an x to the fourth here, right? So they could be combined together. Do I have to worry that I have missed some of the x to the fourth terms? Like with all these dot, dot, dots, I'm just wanting to think about, did I get them all? Or is there any of them that I missed? What do you think? Did I miss any, John? Why not? Yes, it's impossible then to get anything then lower, right? So it's going to keep going up. So notice then I would know the coefficient of the x to the fourth for that series for it as well. I also know what x to the fifth is. I would just need to look at this and make sure that I have found all the multiplications that would add to be those powers. Okay. Here's another one. Third degree Taylor polynomial is there. What do you think? This is a no calculator question. I think all of these are, but if you need to grab your calculator, do arithmetic, I don't care. Tell me the answer. Tell your neighbor, work together. Come on, you're too quiet. You could use the strategy Ron did earlier, right? Like you solve a little equation here, couldn't you? Do it. So third degree, looking here. Okay, but how do I know it's at 4? It's centered at 4. You can see it's sitting right here, like the centers are all 4. So you don't have to do anything else with the 4. There's no other calculation with it. It's got to be just, we would find f of 4 and then f prime of 4 times x plus the second derivative of 4, so on and so on. So really, when you look at this and solve, 3 factorial is 6. So 6 over 512 is 3 over 256. Okay. All right, 2 at once. Where did I lose you? Are you okay with why I'm saying that? Yeah, so this would correspond to the x minus 4 cubed piece here, right? Like that's what I would expect for a Taylor polynomial with a center at 4. Like that's the calculation I would need to be doing to get that term. Now when I look above, like I just want to pick out the same piece, which is this one. And so those two things must be equal. And so really, I'm just taking the coefficient here, which is 1 out of 512, and setting it equal to this. Now, I guess you could put the whole thing there if you wanted, and these would just kind of cancel out. So that's where I got that statement. And 3 factorial is 6, so just multiply both sides by 6. So that cancels out, and I have the third derivative at 4. Okay? You good? Can I go on? All right, let's see if you can do these couple by yourself. Well, your table is fine, but I'm not going to say anything. So there you go. So there is actually the 2. So 79 is the construction we've been doing. So I would want, if I was going to write this out, shouldn't I say f of 3 plus the derivative at 3 times x plus the second derivative at 3 over 2 factorial times x squared, et cetera, et cetera, et cetera. I'm just kind of putting that together. I'm sorry, centered at 3, x minus 3, x minus 3 squared. So what's the answer for 79? I think it's E. Now, if you had a multiple choice question like this, do you notice it's not very helpful to find this term? Like I'm looking at it and going, well, of all the ones with x minus 3, they all have the same one here. So why bother finding that one? Why bother finding this one? Because if it's going to turn out to be one of those numbers, unless it's 6, I'll know it's the right answer. But even just looking at it, I'm going to guess it probably isn't. It's going to be one of these two, which means it's, I don't know, like I just go here and just find that third one and find the answer. So just an observation. That's just kind of a testing with the AP. So here is another question. It's a little different. Related, but the numbers are bigger and you might have to think a little bit more about it. So which one's right? Looking at the second one. So if I want the fourth derivative evaluated at 3, I should look here, right? And I'm going to look out front and I see that there's a negative 1/2. Doesn't that negative 1/2 have to be wrapped up in the second derivative evaluated at 3 and the 2 factorial? Because, did I say 2 factorial? How about the fourth derivative evaluated at 3 and 4 factorial. Okay, so really looking here at this degree is telling us which term we have. Now, when you're looking at this denominator in this 2 factorial, that must have been a simplification, right? That there must have been something with the fourth derivative evaluated at 3 and the 4 factorial that are combined together to end up causing a division by 2 factorial. Okay, so here's the point. If I want the 30th derivative, what is n? Looking at the formula they've given, n is 15. Okay, so the term that we should be looking at, so maybe I write this, like this is the calculation that we would expect to do. The 30th derivative evaluated at 3, x minus 3 to the 30th, and 30 factorial. But with this pattern and whatever's simplifying here, that we're looking here and we're saying, well, if n is 15, I would get something like this, negative 1 to the 16th, x minus 3 to the 30th, and 15 factorial. So this is the calculation we must have done. Sorry, what happened? And this is what we got after it was simplified. So, what is this number then? Take a minute at your table if you didn't get that far. Think about that. So, Vika, that's an important question. Be sure you get that answered. Juliana, can you walk us through what you did? What do you think it is? E, is she right? D, D, E, thanks. D, E, E, Ronit, E, got votes for both E and D. It is one of them. Somebody want to walk me through what you did? You're brave? Let's do it. Say that again. Yes. Yes. Oh, I see. So you're just kind of ignoring this piece, which it's on both sides, right? So that would be the same. So, okay. So what if I just didn't write it? Okay, now what? That's one. That's it. Take them in your table. Talk about it. Yeah, so just to wrap this up, and then I think we might just take a 2-minute break, and then we'll come back and do a little bit more. So, Ben, your question is why the 2n? Like, why is that really then saying n is 15? And it really just then is saying that, do you notice that this is an even pattern of what they're giving us? So it's really almost like if you would take our answer from some of the problems we did earlier where we only had like the evens, we could rewrite it And so that's really all they're writing here in this quantity, the 2n, is like, okay, what's that pattern that I'm seeing? They're rewriting it. But that doesn't mean that there wasn't a fifth derivative term that just happened to be 0 or something like that that's been left out then. So it's like already simplified, and then they're just trying to condense it down into a formula. Okay? Like I said, let's take 2 minutes. You can stand up, get a drink. I'm going to get something to drink too. What I have here for you is a free response question. So this is a full free response question from a BC test. I don't know, I didn't put what year it was, but it's on the screen, but I thought I'd print it real quick for you because that might be a little bit easier. So notice that there's some parts of this question that don't really feel like BC. That's maybe the first observation. Write an equation for the line tangent to the graph of f at 1. Use this line to approximate f of 1.4. Well, doesn't that just feel like locally linear stuff that we've already done? Like that should be easy. That's not a BC question. So one takeaway is, even on the BC test, so let's not do part A, you can do that later if you want, but there's a bunch of AB stuff mixed in. Use a midpoint Riemann sum with 2 subintervals of equal lengths, and even if I just stop right there, doesn't that sound like the chapter 6 test? So I'm going to skip that. That's not a BC question. Euler method, yeah, we don't know that. That's next week. And so we can't answer part C right now. But then part D says, write the second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 1.4. You can do that. Do it. And you can hold on to the sheet because we'll come back to it when we do Euler's method next week. But go ahead and, if you want to leave space on there for A and B, if you want to try that later. But try to answer D right now. So here's the answer. What questions do you have about this? What questions do you have? How many of you got it right? 19.8. Good. But you got the function correct. So a couple observations, right? Isn't this the first derivative, second derivative? I'm sorry, the constant, the first derivative, the second derivative divided by those values. That's really what we should be putting there. We're just constructing it using the information above. It is centered at 1, which means we have to have the quantities of x minus 1 and x minus 1 squared. And then when it says approximate, remember what we're doing is that we are trying to fit a polynomial to a curve that's not a polynomial. So if I choose something close to the center, right, 1.4, I'm going to expect that answer of 19.8 is close to the value of the function. And that's why they're saying f of 4 is about, here, 19.8. Okay? So T2 of 1.4 equals 9.8, and that is about f of 1.4. Don't know. There you go. Pretty sure this was right. So, anything you want to ask me? I'm going to move on to question 2, which is at your table, the next one there. Now, here is a different year, and it has almost an entire question devoted to Taylor series and polynomials. Okay? So let the function f, so function f has a Taylor series that converges for all x in some interval of convergence. It's known that f of 1 is a half and f prime of 1 is negative 1/2. The nth derivative is given by this. So that's a formula then to get the second derivative and third derivative and fourth derivative. So if I want the second derivative, so substitute in 2 for n, whatever that is, third derivative, so on. Okay? So write the first 4 non-zero terms. Do you see that doesn't say degree 4? Right? So be sure you answer the question that correspond to this thing, and notice that it's about x equals 1. Okay? So be sure you get the right quantities. That piece should go fast. This whole thought of this alternating series, this part C, like we'll talk more about alternating series here as we go. And then notice that in part D it's saying show the approximation is within some amount. And so that's starting talking about like error, and that's actually 10.3. So we're kind of on the edge of B, C, and D, but I hope you came up with something for A right now. So let me flip here. So there's A. Sorry. There. So f of x should be this calculation. Notice it did want you to find a general term. And a general term is really just like, what's the pattern? Anybody get all 4? Anybody get all 4 of them? Question? Two squared. Why is it not 2 squared times 2 factorial? You're talking about the denominator? So let's go back. It's over actually what? Only one term would be divided by 2 factorial. In general, what are you dividing by? N factorial. And so that's actually, that should explain. How about this? Let me back up a step. Did you get these parts right? Okay. So when you're trying to write this general formula, I think, is your question here about this piece down here? Okay, so let's just try to look at the pattern that we see. So when you wrote this, did you say this was 8 or did you leave it this way? Okay. So what did you put here? Yeah, it's actually, that's why you're thinking that this piece is wrong, because actually these terms are wrong. This one you luck into getting the right one because 2 factorial and 2 are the same value. Look back at where that's coming from and notice that there's not going to be a factorial. Siri? Is it equal to that? That's fine. What do you have? Yes, that is the same as that. The trouble, though, is if you go one more, it's not going to be 4 factorial. Like, the reason that this looks right to you is because 3 factorial is 3 times 2, and you're going to have then this 2 to a power. If you go one more term and you write it out, like using your pattern, you're going to say that there's a 4 factorial, right? Except a 4 factorial is not really what we would have at all. We should have a 4 times another 2 you're going to get like this extra 3 now, this extra multiple of 3. So it might just be because you stopped here. Like, so I'd encourage you maybe write one more and you'll realize your pattern doesn't fit. Okay? That's a good question because, again, it could look right because of how the factorials are simplifying. But do one more and you'll see it doesn't work. Okay? All right. I think... Can I explain how I got the n? You're asking about this? Well, how about this? Who got the generic term? This general term? Anybody? How many of you got these terms correct? Many more of you. Okay, so how do I take this information and try to write something like this? Let's just talk about that for a minute. Okay? Now, the first thing that we should probably think is, as I'm trying to write this generic term, I'm trying to write the nth term. I need some more space. So I'm trying to write the nth term. So basically, I want something that if n is 1, I'm going to get, well, the first term, and then if n is 2, and then n is 3, and then so on. Or 0, 1, 2, 3, right? Those are our options. So I'm going to substitute something in, I'm going to get those answers. Okay, so when I'm looking at the pattern, do you notice the alternating here? See the alternating? And do you notice that the odd ones are negative? The odd powers have negative coefficients. Doesn't that inspire that statement right now? Negative 1 to the n. The odd powers of n, we'd have a negative sign. Okay? So try to think about building these like in steps. Don't try to write it all at once. So I'm going to try to make the negatives work. Okay, so now I've got the negatives working the way that I'm wanting. Okay? Well, they're all going to have this x minus 1 to the n. And then it's really just a matter of looking at these denominators. Okay, so I see a 2, and then there's this 2 squared 2, 2 cubed 3. Now, if I do one more, and Sadvika, this is really what I was encouraging you to do, the next pattern would be a 2 to the 4th times a 4. Yes, which is why we're going to write this. You would have to put something else up here. So if you would have, here's what you would actually then be writing. So you're on your pattern of wanting this to be 4 factorial down here, right? So if there's a 4 factorial, then there'd be a 3 here, right? Now, if there was a 5 factorial, like, isn't this going to get complicated? Like, think about the step. Like, there would have to be a 4 that's going to cancel out. There's also going to have to be a 3 that cancels out, right? So now there's a 12. So how are you going to write this? You're going to have to write it as a part of a factorial. And it's going to simplify back to this. Try it if you want. So back to this, though. If this is a pattern, if I'm going to keep getting these 2, 3, 4, 5, etc., do you notice that that's the n? So all you're really doing is looking at your work here And you're going, okay, how would I have constructed it such that I get certain pieces? And that's how they're writing it. Okay? So if you could try to write that out, if you don't see it, ask me and I'll show you. Okay? So I think this probably needs to be our stopping point. Again, we'll talk about some of these other aspects to it. I think what I'd like to do today, even though everyone's not here, no, I'll do it on Tuesday. So I have for you to borrow a review book that we can pull some other questions out of. So for the rest of the semester, but I'll give it to you next time. I'm not going to keep you here to get that book today. We don't need it for any of the homework we're doing. So 10.2, I don't know if we have totally finished 10.2. I might start 10.3 on Tuesday, but we probably need a quiz soon on 10.1 and 10.2. Okay? Please. Okay. Yes, I will. Oh, please no. Oh.